Greetings, building science enthusiasts, and welcome back to the Building Science Podcast. This episode is brought to you by Ultra Air, whole house ventilating dehumidifiers. Here at Positive Energy, we've been working with these dehumidifiers for years on many of our integrated mechanical designs, and we've seen such great results for both the health and comfort of our clients. We even have an Ultra Air dehumidifier in our office, and we absolutely love it. When you're working with an airtight and well-insulated building, you quickly notice the outdoor air infiltration restrictions that occur, which allows pollutants and moisture levels to accumulate inside. So when you think about it, properly controlling that moisture in your home will definitely improve the effectiveness of your air sealing and insulation efforts, and will definitely improve the health and comfort for your client, your family, you. Just imagine being able to run your air conditioner at a higher temperature without feeling uncomfortable, and knowing that this improved comfort is coupled with fresh filtered air. These are just a few of the many benefits of incorporating the Ultra Air dehumidifiers into your home or your project. It really is an easy choice to make. To learn more about the best strategy for controlling moisture in your home, check out ultra-air.com, that's air with an E at the end, and see how a whole house ventilating dehumidifier can work for your home or project.
Welcome to the Building Science Podcast. Welcome to the Building Science Podcast.
Bringing the human factor to construction, design, and architecture. Brought to you by Positive Energy in Austin, Texas.
Okay, hello and welcome everybody. Welcome back to the Building Science Podcast. Today's topic is humidity issues in spray foam attic assemblies. And this is one of the first episodes that has actually been motivated by, let's call it the mainstream building science media. And we have a couple of guests on the show today, one of which is a big part of the mainstream building science media, at least in my opinion. And that is Dr. Allison Bales with Energy Vanguard. He's joining us live from Atlanta, Georgia. Say hello, Allison.
Hello, Allison.
Okay, so Allison is the chief juggler at Energy Vanguard, and he has some really smart people that run the show there. No. Just kidding. Allison is, in fact, a juggler, but he is the principal of Energy Vanguard, and he is also the author of the Energy Vanguard blog. And I'm pretty sure a lot of you listening are already familiar with him and know that he is a key resource in our industry right now as far as education and also for advocacy for good practices. So my other guest speaker is Keith Simon. Keith Simon is with Building Exterior Solutions, a division of Terracon, and Building Exterior Solutions is an envelope consulting company. And Keith is also an adjunct faculty at UT School of Architecture. And before we begin, guys, I'd like to just give you each an opportunity, so we'll start with you, Allison. If you would like to say something you wish I had said about you or Energy Vanguard, now's your chance.
About me or Energy Vanguard? Well, gosh, when I saw that there was somebody named Allison on here, I thought there was going to be some woman on the show today. And I was looking forward to that. But then I found out it was just me.
Okay, so what about Energy Vanguard? What does Energy Vanguard do?
Oh, gosh, that's a hard question. Energy Vanguard. Well, we do training, consulting, we do HVAC design, and I write the Energy Vanguard blog, and we're a HERS provider. And we sell used clothing in a department store basement. Wait, no, we don't do that.
Okay, very good. I get it. So, yeah, it's for those of us, Allison and I included. Keith's with a slightly larger company now, but it's really quite a feat to pull off having a company based solely in the realm of building science in today's market. It's so congratulations to you and I, Allison. Keith, anything you'd like to add about Building Exterior Solutions? What do you do there?
Sure, we're full building enclosure consultants, so we work on the design side, supporting architects or project teams with peer review design assistance, hygrothermal modeling of assemblies. We do a lot of our construction observation, pre-construction meetings, mock-ups. That's probably our bread and butter, and then quite a bit of water testing and other types of testing. On the verification and investigation side. Failure investigations is another big part of what we do. And although it can be a very intense and stressful situation when that happens, it's always fascinating. We always learn something really interesting. So on the one side, our work is extremely nitty gritty and practical, watching a bead of sealant and how it's tooled. On the other hand, we also, like you guys, get to investigate really, really hard questions that are not readily apparent in the industry. And today's focus is one of those that I think is very fascinating, very challenging, and very pertinent.
Yeah. Okay, let's jump right into it. So today we're going to be talking about humidity issues in spray foam attics. And by issues specifically, I mean the problem with moisture and durability of the roof decks. And before we jump right in, I want to get very clear that when it comes to the topic today, right, so spray foam assemblies in attics, there are other dimensions of the spray foam debate, I guess, that's going on in the industry right now. And what we're focusing on today is strictly material durability. We're not talking about the potential for indoor air quality concerns. So I'd just like to make that clear. Allison, I'm going to start with you since you have a couple of nice blog articles on this topic. Would you be willing to try to give our audience an overview of what's going on?
Sure.
And then we'll take it step by step.
Yeah. Well, the issue came up for us a couple years ago when we got a call from a homeowner here in the Atlanta area where we're based, and we went. She had a house that had been remodeled about 5 years earlier. They got open cell spray foam installed at the roof line, and so they had the sealed attic with open cell spray foam. And we put some data loggers in there and found some really interesting results. We found that at the attic floor, the humidity was much lower than at the ridge of the attic, near the peak of the attic. In fact, let's see, let me pull my data up here so I can know what I'm talking about. At the ridge, the relative humidity would be low at night, and then and this is summertime I'm talking about. During the day, the relative humidity would go up, and it would hit about 90% on some days at the peak of the attic, the ridge, and at the floor of the attic, it would get to only about 70% relative humidity. Now,
how about the living area? How about the conditioned space?
The living area stayed around 50% all day long. Bounce out, go up and down a little bit within just a few percent. But relative humidity, if you've read my blog at all, you know that I'm not a fan of just talking about relative humidity because that can be confusing because the temperature is changing too. In fact, in the spray foam attic, you're going to have a more dramatic temperature change than in the living space of the house. And the better the spray foam attic is done, the less change you'll have, but still you're going to have more than in the house. Right. Let me try to summarize a little bit better here.
Recalibrate that as far as dew point. Is that where you're going?
Yeah, so dew point. So we also measured dew point, and we saw that the dew point also went through these daily cycles of going up with the outdoor temperature during the day and then down at night. So it wasn't just a matter of temperature changes causing the relative humidity to go up. It was the actual amount of water vapor in the attic was increasing through the day, and more at the ridge than at the floor. So this is what we saw. The data are pretty clear. There is water vapor. The amount of water vapor in the air of the attic is increasing through the day, and there is a lot of stratification. It increases more at the ridge than at the floor of the attic. So
understood. And
this is related to the durability issues that you talked about, because when you pull the foam off of the attic, in some cases, if you pull the foam off, you'll see that there's corrosion of the nails and the clips holding the OSB together, the roof decking, or
apart actually.
Yeah, right.
Spacer clips.
The spacer clips for the OSB roof decking. The wood itself in the roof decking is absorbing moisture and in some cases rots and has to be replaced. This the wood that rots and has to be replaced usually is at the ridge. It's pretty much always at the ridge, about from the ridge down about a foot. This is something from Joe Lstiburek. Joe Lstiburek at Building Science Corporation has been involved in a lot of investigations of building science issues and a lot of rotting roof issues and things like that. And when it comes to the spray foam addicts with open cell spray foam in hot, humid, or mixed humid climates, and I'm talking about Atlanta for this house that I mentioned. That's climate zone 3, mixed humid. But it's happening a lot in south of us as well. A lot of it going on in Florida, and the moisture. What's happening is you're getting this moisture increasing in the air through the day at the ridge, and then at night it disappears. Where does it go? Well, where it's going is through the foam, because open cell spray foam allows the water vapor, the moisture, to move through it, and it goes to the wood, the roof decking, which is usually OSB. And that wood holds the moisture at night. In the daytime, when the sun comes out and heats up the roof, it drives that moisture back down into the attic and into the air, and you get a lot more humidity near the ridge because, well, we don't know exactly which plays a bigger role, but there's both thermal buoyancy and hydric buoyancy. So let me quickly explain the difference between those two. Thermal buoyancy is if you have a bigger volume of air and one part of that air gets heated up, the part of that air that gets heated up becomes less dense, and it will float. It will be more buoyant, and it will rise higher in that space. That's thermal buoyancy. There's also talk about hydric buoyancy happening here, and that is because air is made up of two main components. It's dry air, which is mostly nitrogen and oxygen, and water vapor. The amount of water vapor changes dramatically, or can change dramatically, but water vapor also is lighter than the dry air part of air. It has a molecular weight of 18. Dry air has a molecular weight of about 29. So hydric buoyancy would be the water vapor rising because water vapor is a lighter molecule than the dry air components. That's right. The hydric buoyancy. Hydric has to do with water. So not sure if that's happening or not. What we do know is that there is definitely stratification. We're seeing more moisture at the top than at the bottom. So it could be just thermal buoyancy, it could be just hydric buoyancy, it could be a combination. Joe Lstiburek calls it the ping pong effect. So let me back up a little bit now and say, what we found, what we're seeing, and this is not just us, other people are seeing this as well, in spray foam addicts with open cell spray foam, you're getting a lot of humidity and you're getting stratification of that humidity. Higher humidity at the top and lower at the bottom. And it cycles. Every day it goes up. In the summertime, during the hot part of the day, the water vapor in the air goes up, the humidity goes up, and then it goes down at night when things cool off. It's going down at night because the water vapor in the air gets pulled towards the OSB. My friend Foster Lyons, who's got a background in chemical engineering, says that it's because of the chemical potential of the wood. The water vapor is attracted to the wood. There's a high chemical potential there. And so the water vapor is pulled through the foam because it likes to hang out with the wood. Wood is hygroscopic. It's another way of talking about hygroscopic materials. Hygroscopic materials are materials that can attract water vapor out of the air and cause the water vapor to adsorb, with a D, A-D-S-O-R-B, to the surfaces of that material.
And this is not the outer surface for you listening. This is the pores of the wood, the lumens, things like that.
Which OSB is wood, or was wood. And it has lots of surface area, and it has lots of pores, and all the surfaces inside the pores and on the surface of the material itself, there's a lot of place for water vapor to bond. And So that's what's causing that to happen. And when it cools off at night, it pulls that water vapor out of the air. And when it heats up, that drives the water vapor back into the air.
So I think we should define for your listeners a little bit more which types of roofs we're talking about. In other words, these are attic spaces with open cell spray foam up at the roof deck that are not vented. Is that right? I mean, it's not. We're not talking about a cathedral ceiling that's unvented, because then there's conditioned space below it, which could take the moisture out of the air. And is it also not talking about a traditional vented attic space where it would allow the humidity to escape through the ridge? But is that right? And then we're also talking about, this could be a new construction that's designed that way, but this could also occur in a renovation of a traditional vented attic space where you closed up the venting and then put open cell spray foam at the deck with best intentions. You could be creating this situation.
Correct.
Yep, you nailed it.
Yeah, and we will talk about the cathedralized ceilings as we get deeper into this. So Allison, that was a great introduction. What he was talking about, you guys, you've heard it on other episodes of the podcast, was bound water, which is the fourth state of water in some sense. It's water with a material. And the reason it's so concerning is because when you bind enough water to an organic material like wood, you create circumstances for mold and fungus, to cause rot. So long-term exposure to moisture is key to, or avoiding long-term exposure to moisture is key to keeping materials durable. So that's why it's a big deal. And you did mention the climate zone dependence in there. You said hot, humid, mixed humid. What about as we go up in climate zones, 4, 5, things like that? Does the problem go away? Does it get worse? What are we thinking about that?
I think it's more a problem with the warmer climates. The farther north you go into the colder climates, the less heat there is in the summer. And so the less cycling you're going to see from the heat driving out. But even in the north, attics get just as hot on the hot days. There just aren't as many hot days. And so there's probably not going to be as much total time when the roof is going to be wet.
Well, one thing I think that's really interesting about this is that, Allison, I don't know if you have the same issue in Georgia, but here in Texas, when people hear open or hear closed cell foam, there's a general rule of thumb that that's the wrong kind of foam for our climate, that you always want to use open cell. And it's just so short-sighted because it depends so much, right? Mm-hmm. There are times where here, for example, in a roof assembly, that closed cell may be the appropriate choice. I've even done simulations of wall assemblies where I've advised closed cell instead of open cell, just to get absolutely against a wall, like, oh my gosh, no, not in our climate. That is ludicrous. Just the whole thought. And certainly under floor, there's, more often you'd want to do closed cell than open cell. So it's that mindset of some kind of rule of thumb that we're sort of up against here.
Yeah, and you make a really good point, and the difference between open cell and closed cell spray foam is important, because this is only happening with open cell spray foam because it is permeable enough for the water vapor to move through it and find the wood decking. Closed cell spray foam, that's not going to happen with, because it's not permeable like that. And that makes me want to go. I need to go back and correct something I said just a minute ago about climate zones. Climate zone 4 is probably pretty similar to climate zone 3, but when you get into climate zone 5 and higher, you're not supposed to. The code says if you use open cell spray foam in an attic situation like this, then you need to put a vapor retarder over it, and that would eliminate or reduce the amount of water vapor moving in and out that you would see. That may be the main reason that you don't see it in climate zones 5 and higher.
Well, right, in those cold climate zones, the rule of thumb is to always use closed cell, so they may just never, it must be really rare that they would do this kind of assembly in a cold zone.
Hey, let me interject real quick briefly, just to make sure everyone's clear on the physical differences between open and closed cell. So they're both made out of polyurethane. They are both basically the same material as a bowling ball, but it's been aerated. It's full of bubbles. So like frothy bowling ball material, it's polyurethane. A couple of, I guess, 3 physical properties for each. I'll limit it to. One is the pounds per cubic foot. Open cell is like a half to an 8/10 of a pound per cubic foot, whereas closed cell is much more dense. It's more like 2 pounds per cubic foot. One simple test, if you're standing in front of this yellow foam substance or whatever color it might be on this building material, you tap it with your fingertip. You're like, let's say your index finger, tap it hard. If it just kind of bounces off, that's closed cell. If it sticks in, that's open cell. And what you're measuring there is the density, or you're experiencing. Then there's the R value. Open cell has a range, roughly 3.5 to 4.5. What's R value, Allison? So it's square inches per degree Fahrenheit per hour divided by BTUs. Anyway, and
I always have to work back from the equation.
Yes, exactly. That's what I was trying to do. I closed my eyes on that one. So anyway, we just say R value. So R value 3.5 to 4.5, and closed cell, that was open cell. Closed cell is 6 to 7 R value. And the big difference that's of interest today is this perm rating. And let's just keep it simple and say a perm rating is a evaluation of how easily water vapor can move through a material. The higher the perm rating, the more easily water vapor can move through. And at the thicknesses we commonly see in attics, perm ratings are on the order of 10, let's say, for 5 inches on open cell. And if you had 2 inches of closed cell, the perm rating, instead of being 10, it would be 0.8. So quite a bit, roughly an order of magnitude lower. And so that's why Keith, why you both were saying is less issue with water vapor accumulation in a building material that has a lower perm rating insulation on it.
Well, you should also probably mention their ability to withstand air transport too.
Ah, good. Please.
We'll just, so Christoph mentioned their resistance to heat flow, R value, which is important. Their resistance to vapor permeance, their potential as a vapor retarder. There's also their ability to withstand air transport, so they can be used as a great part of a greater assemblies and systems to be a continuous air barrier. And both open cell and closed cell can achieve that at a certain thickness. And I can't remember offhand. Let's say an inch or so of closed cell versus maybe you need 3 or 4 inches of open cell.
I think it's 3.5 to 4. What do you think, Allison? Do you remember the thickness?
So the last couple of years I've been going to the Air Barrier Association conference, and if you talk to the guys there, well, it depends on who you talk to, but so the Air Barrier Association of America, ABAA, tests materials to classify them as an air barrier or not. Closed cell spray foam, I'm pretty sure, has been tested and does qualify as an air barrier material. Open cell spray foam has not been tested and certified as an air barrier material. If you talk to the spray foam guys, they'll all tell you that yes, open cell spray foam is an air barrier. If you talk to some of the guys at the ABAA, they'll say the open cell hasn't been tested. It may or may not be.
But at some thickness, it's, well...
But you've done a lot of whole building air leakage testing of homes with spray foam,
yes.
Open cell spray foam, and you've seen it been able to achieve certain benchmarks, I assume.
Absolutely, yeah. So you'll get homes that are easily hitting blower door scores of 2 to 3 ACH 50s.
But what you're testing there is you are testing an enclosure. You're not testing the material. When open cell spray foam is used at a great enough thickness in contact with OSB and drywall and the other materials and the assemblies and the enclosure, then yes, the whole thing turns out to be tight enough.
Which is why it's so common in the market, frankly.
And yes, I mean, even though open cell spray foam may not have been tested and certified as an air barrier material, I can tell you from having tested, like you guys are saying, a lot of homes with open cell spray foam that they definitely are tighter.
And we'd be, just to close the door on this, we'd be remiss if we also didn't mention the property of being a water resistive barrier, because while open cell spray foam can never really be a water resistive barrier, closed cell foam actually can act as one. Under certain circumstances, you wouldn't want it directly applied to a material. You'd want an air barrier, an air gap, say behind the cladding, between the spray foam and the cladding, to allow it to act as a water resistive barrier. And there's a lot of issues with the installation of it. So I'm not sure I would ever actually recommend it and drop a water resistant barrier behind it. But it's worth noting that it does have the closed cell spray foam has water resistive capability that open cell does not.
Yeah, absolutely. And there are higher densities, right? So I said roughly open cells like 1/2 and closed cells like 2. Well, you can go closed cell up to 4 pounds per cubic foot. And those even are better as water resistant barriers.
Right, and I was just going to mention that issue because open cell spray foam and closed cell spray foam, that's one way of classifying the two materials, and 1/2 pound density and 2 pound density is another way. And a third way that you'll hear some contractors talk about this is low density foam, which is open cell, or medium density foam, which was closed cell. Yeah. And some people call closed cell spray foam high density, but it's actually the stuff that we use for insulation is medium density. That's 2 pound, because the 4 pound foam is the high density, and that's used usually for roofing, not for insulation.
One more common term you'll hear out there is canned foam, and canned foam
or
gun foam, which you can pick up at, say, Home Depot or something like that, and sometimes is used around the perimeter of your windows or doors. That is always closed cell.
All right, so water. Let's discuss this moisture, this thing that's aiding digestion and causing durability issues. Where is this water coming from? Where one of you want to discuss that? Talk about that?
Man, that's the $64,000 question, and
yeah.
We don't really know. We know how to solve the problem. Let me back up a little bit. Joe Lstiburek says that he knows where it's coming from. He is absolutely certain that the moisture is coming from the house, although some people think that it could be coming from the roof, because at nighttime when the roof cools down, it can, in a humid climate, can get dew on it, and that dew sitting there when the sun comes out, some of it can evaporate back outward to the outdoor air, but some of it could be driven downward. And if the materials are permeable enough, that could be driven all the way down into the attic. So some people think that at least some of the moisture could be coming from above on the roof. Joe thinks it's coming from the house.
Interesting. And so from internal sources, just want to remind everyone we're talking about breathing, people cooking, showering, plants, pets.
And we know that the ceiling plane is never well sealed.
Right.
So you have an attic space above your ceiling and then the living below. So the temperature, the heat, all your humidity sources are going to find their way into that attic most likely.
Right. So the question is really not whether it's coming from indoors, it's just whether there's also a component coming from outdoors or not. It sounded like you were alluding to, and just for quantifying, you guys, listeners, internal sources, it's typically between, let's say, 10 and 30 pounds of water a day, internal source. So these are not really small amounts. I mean, roughly a pound an hour, up to about a pound an hour of water. And a pound is a pint, roughly speaking.
I mean, 10 to 30 pounds a day would be for like a family of 4 or 5.
Oh, a 3-bedroom house. Yes, correct.
So
Thank you for.
I mean, if you've got 2 people in the house, you're not going to get quite that much. But yeah, it is still significant. You get a significant amount of moisture just from people doing their daily things in the house.
Yeah, and what I was getting at, it sounded like you were alluding to this very pragmatic approach, which is wherever it's coming from, it exists, and it's getting into the material, it's getting into the roof deck. And this kind of brings us to the heart of the matter, which, we know we have wood, we know we have moisture. What do we do about it? Right? How do we provide drying potential for this roof deck?
Right, so solutions, one is to use closed cell instead of open cell. Another is to condition that attic space. A third would be to add ventilation.
Like vapor venting at the ridge?
Yeah, vapor venting at the ridge. Now, that being said, so we don't consult too much in single-family residential, so I'd be curious to hear from you guys if you've tried solutions and if those are the ones you would go to, or if there's others out there.
And conditioning, we should quantify or qualify what that means, conditioning the attic.
One of the things that a lot of spray foam contractors do is when they put spray foam in an attic, they'll have the HVAC contractor dump a little bit of supply air into the attic. And that will be conditioning the attic. That will help dry it out. Now, if you've got ducts down low in the attic and your moisture is hanging out near the ridge, that may not help you as much as you want. But it will definitely help because you're adding a little bit of air. It will be adding drier air, and the pressure in the attic will go positive. So some of the excess air will be forced down through the unsealed penetrations and stuff into the living space. If there's odors up there, then that can lead to people saying, hey, where are these odors from? What Joe's trying to do is to make it legal to put a return in the attic, and that way you could put a return up near the ridge so you can pull the humid air from the ridge into the air conditioning system. And let's back up and make sure that everybody understands we're talking about spray foam attics in summertime. We're not talking about wintertime. Wintertime is a whole different issue, but this is summertime, so you've got the excess humidity near the ridge on hot days in the summer. And so if you pull that in with your air conditioner and run it through the air conditioner, then that helps to dehumidify it. Currently, that's not allowed by code, though, because you could be feeding fire if the house catches on fire.
And same thing with a dedicated supply air duct into an attic. If you do that, you trigger the need for fire-rated assemblies or fire protection dampers. So you have to rely on incidental leakage.
And not only ignition barriers, but thermal barriers. When you get into using your air conditioning system to condition the attic, you run into those kinds of issues. And Joe's been working with the International Code Council, the ICC, trying to get the code changed so that we can do some of these things a little bit easier. Now, Joe wrote a great article about this topic a couple years ago. It's called Cool Hand Luke Does Attics.
Right.
And in there, he talks about this issue of what's allowed by the code and what's not. And he even quotes the code so you can see what the code actually says. Trying to use your ducts intentionally to condition the air in the attic is a way to go. And he said, but we didn't used to have to do this because it used to be that the ducts had enough leakage by themselves that we didn't have to do anything extra. There was a little bit of leakage on the return side. There was a little bit of leakage on the supply side, and everybody was okay with that because there weren't any requirements for duct leakage back then. We were spraying foam in attics, and everything was good. But then we started getting testing requirements for duct leakage, and now ducts have to be tight, even in a spray foam attic. In his article, Cool Hand Luke Does Attics, or Meets Attics, I can't remember, he talked about we didn't have this problem with spray foam attics 10, 15 years ago because we didn't have duct leakage testing requirements. Now
Right.
Ducts have to be tight even in spray foam attics, and what happens is that the moisture builds up there.
And by the way, so for listeners, there might be people with an older installation with spray foam at the roof deck, and they haven't had problems for many years, and it might be that they have enough incidental or accidental duct leakage to be preventing this problem. However, there are other problems from incidental duct leakage, other potential problems.
So another solution is just to do continuous insulation. In other words, just insulate on top of the roof deck, not insulate under the roof deck. And, that's continuous insulation has its own challenges and times when you do and don't want to do it. But in general, the reason why conceptually continuous insulation is such a great concept is because you avoid all these issues that all your dew point is outboard of all your organic materials.
Correct.
You're not concerned about trapping any moisture because it doesn't get in. Of course, that assumes a lack of thermal bridges and with your cladding attachments and your bridge vent and whatnot. So,
and that does seem to be inexorably where the industry's moving, is toward exterior insulation. While we're talking about ventilating the attic, let me go back to that. So we talked about a supply air duct, a return air duct. Designers like us that are doing mechanical designs in humid climates, we are always recommending dedicated dehumidification systems. And one way to get around this issue of, how do I handle the, fire code requirements as soon as I put a ducted system up there, you could put a dedicated attic dehumidifier in. That would absolutely solve the problem. it's not necessarily the most cost-effective way. I mean, it's a couple $100 for a dedicated DHU, and you'd have to provide a condensate drain, which actually would probably be already up there. Just want to make sure that gets brought out. So increased exposure to drying potential could come from supply air, return air, or dehumidification. It could also come from continuous insulation. It could also come from vapor venting at the ridge.
So this is the Joe Lstiburek had the article about how to do this as well, right? So like we're all familiar probably with ridge vents, which allow air to vent through the ridge, and along with the air vents vapor and heat as well. So that's great if it's a vented attic space, but if it's an unvented attic space, you don't want to lose that air and heat. It wouldn't be an energy efficient thing to do. But we do have this problem of vapor buildup right up at the ridge there that we've been talking about. And so Joe Lstiburek has come out with a strategy. And unlike Allison, I haven't memorized the title of his article where he talks about a vapor open but air closed little ridge cap, which is
the title of that article is called, get it, wait for it, it's called Venting Vapor.
Venting Vapor. Tricky. Yeah, and actually that's Andy Ask's house in the book there. Andy Ask, of course, who wrote H2No, Moisture and Dehumidification. Okay, so besides supply ducts, return ducts, and dedicated dehumidification in the attic, or a dedicated dehumidification duct supplying the attic, right? So that was 4 different things: supply, return, dehu duct, dedicated dehu. There's this question, right? So many of our clients already enjoy houses, and I mean both of our clients, Allison. As mechanical designers, we're specifying dedicated dehumidification systems. You know, we're specifying it in all of our designs. And there is this question or this idea that, first of all, the dedicated dehumidifier addresses the source of the moisture directly. It's saying, look, that 10 to 30 pounds of moisture a day, I'm going to go ahead and remedy that. I'm going to take care of that. Maybe not all of it, right? Because you're going to set your dehumidifier, say, at 55% or something. But the question is, and I think we might need research on this, the question is whether or not, if I have a dedicated dehumidifier maintaining a dry air mass inside my house, if that is going to prevent this condition from occurring.
In my experience, the answer is yes, because we did that in the house here in Atlanta, and it solved the problem. So
I think we need more than one data point, but I'm optimistic as well that would solve the problem. So the tricky part is there's a few, three, let me say two main things that we need to deal with now. And I say two because one of them was unconditioned or vented attics. So this issue is not going to occur in an unconditioned or vented attic. Now, that's not to say that those are better assemblies or more climate zone appropriate. Certainly they're less appropriate if you have any mechanical equipment or distribution up there. But for the topic at hand, that's not the case. So there are two. There are low slope roofs, flat roof, low slope roof. That's one topic. And the second one is vaulted ceilings. So let's start with vaulted ceilings. So we have the same situation that Allison described at the beginning of the podcast here, which is we have moisture. Well, let me just say the assemblies. We have roofing, underlayment, roof deck material, and then we have a layer of open cell spray foam. But now, instead of having an open attic space below, we have sheetrock on the other side of the rafter. So what do we do about that, you guys? How would we address that issue? We obviously can't put a supply duct in there, a return duct in there.
In my opinion, it's not going to be a problem because the paint and the drywall offer enough extra resistance to the moisture diffusion that you're not going to see that kind of cycling that you see if you just have the bare open cell foam next to the air.
I see. So it's the air transported moisture from the conditioned space up and in that is going to be prevented. Now, if you have ceiling cans or a lot of fixtures in that, you're going to advocate, or you're going to say maybe it is more of a problem now? Or
I'm not going to advocate anything except getting rid of those can lights if you got lots of can lights up there.
Yeah. We have surface mount LED cans now, so there's no need for them.
There's also it may be helping you in the other direction, which is
the can.
Well, no, you're you may be doing more to condition that unvented space, because you're now, all that's separating the conditioned environment is a piece of drywall. So it's almost like your dedicated dehumidifier, which is going to draw more of the moisture and condition it and get it out. That may be an effect as well.
Right. But it could, so I can actually see a logic that states that what I want to do is I want to provide for mixing of the small air mass that's up in my attic. Oh, interesting. I guess we need to qualify here. I'm thinking something like a 2x10 rafter with 5 inches of open cell spray foam on the roof deck and leaving a 4.5 inch, roughly, air gap below it. This is definitely different if you fully fill your rafters, shave the foam and put your sheetrock up. Because then, what I was going to say was if I could get some air circulation up into that 4.5 inch air gap, that would help with moisture transport out of that space.
Now, what further confuses it is, okay, we're talking about asphalt shingles, felt paper on roof decking, but say it's a metal deck and you want to use a high temperature self-adhered underlayment. Well, they only make those that are class 1 vapor retarders. They don't make those underlayments that are vapor permeable. So there's a lot of concern about the top side of your deck being a class 1 vapor retarder and then spray foam underneath, which is lowering the drying potential to some degree. And without further analysis, I don't know whether that self-adhered underlayment is helping or hurting you.
Yeah. There's the other idea or the other concern here. What about flat roofs with open cell spray foam? The way I'm relating to this, the way I'm understanding this, is that ping pong water effect is not going to be concentrating the moisture load at the peak as it would be in a pitched roof.
Not if there's not a peak.
Correct. And the question is whether or not the lower density of moisture accumulation in the decking is enough to provide an issue or not. Because in a flat roof situation, it's very unlikely to have, or it's more unlikely to have, an actual attic below it. It's almost certainly going to be roof, rafter, sheetrock.
So we don't see, we see in the multifamily world, we see a lot of flat roofs, steep slope roofing as well in multifamily, but a lot of flat roofs in multifamily. We never really see spray foam, but we've been engaged in a pretty thorough analysis that's ongoing because there's the desire from the multifamily builders to fill up the attic space with cellulose or something similar, because there's air in there, they have to sprinkler it. They have to put sprinkler piping, which is very expensive. So if they fill it all with insulation, they don't have to, and it can save them money. But the problem is they're drawing that dew point, and then they want to just limit the amount of continuous insulation above the roof deck. So they want to do like 1 inch of polyiso above and then 24 inches of cellulose below, drawing the dew point down. And we're seeing real problems with that, potential problems. And so we're constantly working with what are the solutions to that. I mean, the easy one is just stick to the prescriptive requirements in the code and do your R20 or R25 above deck. Eliminate the insulation below and you're good to go. Or what is the right proportion of above and below? There's other things you can do, like allowing an air gap, venting, etc. But that's the roofing question that we're being faced with right now by sort of builders nationally.
Yeah.
Where they're building in multiple states and they don't know what a durable roof assembly is for that scenario.
So we're getting towards the wrap up, you guys. Let's try to get some final thoughts here. One topic as part of the wrap-up is how big of a problem is this on existing homes that have been built in the last 10 years with open cell spray foam and unknown amounts of incidental leakage that's providing some drying potential. Any suggestions or insight into that?
Ooh, I don't know. That's a good question. It's something that when people ask me about it, if a homeowner has spray foam in their attic and they've read my article and they want to know, well, what can I do? I tell them, get yourself a digital thermohygrometer with a remote sensor and put the remote sensor or maybe a couple up in the attic. Especially if you only put one up there, put it near the top of the attic up high and monitor the humidity there. If your humidity is doing okay with as things are, then you're fine. You don't need to do anything. But if you're seeing the kind of humidity levels that we saw in that house here in Atlanta, then you probably need to think about some kind of way of conditioning that attic.
Excellent. And for listeners, we can provide in a link to a suitable RHT sensor that can be Bluetooth connected that aren't crazy expensive for you to make that happen. We'll try to put that in our show notes. Keith, so you are, among your other things, a woofy god, a woofy modeler. What do you consider about the role of woofy in this situation?
I think woofy is a great tool to help us figure this stuff out. And but we have to know its limitations, of course. And like any software, it's a great tool to have in our tool belt, but it's not the only answer. We have to balance it with experience and knowledge and the rest of it. But I can tell you, and I would say the same thing about rules of thumb. So rules of thumb are great as long as we're aware of their limitations. And closed cell versus open cell is a great example in this climate that there are times when each is appropriate. A certain thickness of each one might be appropriate. And either we can figure that out by trial and error and experience, or we can use our knowledge base and then use woofy to figure things out. So I think woofy is really one of the keys to these really tough questions that are out there.
Yeah, I agree. So final question, and then we'll wrap up, you guys. We'll end this podcast. What do we say to architects, builders, to project teams generally, building in climate zones 1 to 4, new construction? What's the best practice now? Has this emerging issue changed what we consider to be best practice?
So I would say, well, I'll quote Peter Pfeiffer, who once said about spray foam that every once in a while there's a material that enters the industry that just transforms the industry, and he felt like spray foam was it at a certain point in time. I feel like now we're moving beyond that. I would not consider spray foam, it's a whole lot better than most code building we see, but, going towards continuous insulation is another level of high performance. That being said, I think, there are certain spray foam has certain properties that it makes it applicable in some situations that no other material can. So going back to the tool belt analogy, it's always something we want to have in our arsenal, but I don't see it as like the apex of insulation by any means. Yeah,
spray foam has the benefit to the industry of being a direct one-to-one product replacement or subcontractor replacement that enables conditioned attics, makes them very easy to pull off, and enables lower enclosure leakage numbers so you meet code or get lower than code. And that's been a very strong reason for its uptake in the industry. Closed cell spray foam at the roof deck, a layer of it, an inch with an open cell over it, that would also remedy this problem using the tool of spray foam.
Yeah, it wouldn't even have to be 2 spray foams. It could be 1 or 2 inches of closed cell and then bats or cellulose or something. Mm-hmm, mm-hmm. But I think up to 5 inches is probably okay. Although I guess it gets expensive after an inch or so.
5 inches of closed cell. Allison, any final comments? Any advice for project teams out there looking to insulate an attic right now?
Yes, mine would be that you have to think carefully about open cell spray foam in attics like this, because we know that there are moisture problems that can occur in humid climates in the summertime. So you've got to plan on conditioning those attics or designing the enclosure differently so that either you don't have the open cell, you use closed cell instead, or you put foam board or Roxol on top of the roof deck, or or you use a vapor retarder, or you've got to do something. You've got to address it one way or another.
Mm-hmm. Well said. With that, everyone, we will go ahead and end this episode. Keith, thank you very much for being here in our studio. And Allison, thank you for calling in from Atlanta. And listeners, thank you for tuning in and being interested in building science generally. Thank you.
Thank you.
This episode is brought to you by Ultra Air whole house ventilating dehumidifiers. Here at Positive Energy, we've been working with these dehumidifiers for years on many of our integrated mechanical designs, and we've seen such great results for both the health and comfort of our clients. We even have an Ultra Air dehumidifier in our office, and we absolutely love it. When you're working with an airtight and well-insulated building, you quickly notice the outdoor air infiltration restrictions that occur, which allows pollutants and moisture levels to accumulate inside. So when you think about it, properly controlling that moisture in your home will definitely improve the effectiveness of your air sealing and insulation efforts, and will definitely improve the health and comfort for your client, your family, you. Just imagine being able to run your air conditioner at a higher temperature without feeling uncomfortable, and knowing that this improved comfort is coupled with fresh filtered air. These are just a few of the many benefits of incorporating the Ultra Air dehumidifiers into your home or your project. It really is an easy choice to make. To learn more about the best strategy for controlling moisture in your home, check out ultra-air.com, that's air with an E at the end, and see how a whole house ventilating dehumidifier can work for your home or project.